Let's talk about balancing reactions. Before we start doing examples in balancing reactions, it's important to understand one of the most important principles in chemistry. This principle is called law of mass conservation. That means that mass is always conserved. In chemistry, mass is always conserved. That is not true in, say, nuclear reactions, or for example in the sun, when maybe some of you may know the Einstein's equation where mass becomes energy or vice versa, but that in chemistry never happens, or I would say it would have to be very heavy elements. So pretty much in chemistry we can ignore this equation because mass is always conserved. In any reaction, mass is always conserved, and that principle can be understood if we give an example. Say that calcium oxide and carbon dioxide are mixed in these proportions. Notice that these are the actual molecular masses of each. So if we mix 1 mole of each, if we mix 56 grams of calcium oxide and 44 grams of carbon dioxide, we will obtain 100.08 grams of calcium carbonate. And this amount of mass is always the addition of these two. So it cannot be that after reaction the total addition of masses of reactants and products, even if there are leftovers, it cannot be that the mass changes. The total mass is always conserved. So the mass conserves. However, there's something else that conserves as well. Notice that the atoms also conserve. There is 1 calcium here, there is 1 calcium here. There is 1 carbon here, there is 1 carbon here. There is 1 plus 2, 3 oxygens, there is 3 oxygens. So the identity and number of elements is also conserved in a reaction. And that is the basic principle that we will use to balance reactions. So what a balanced reaction tells us is, if you will, a recipe. It tells you the proportion that every time this reaction happens, there will be 1 molecule of oxygen reacting with 2 molecules of hydrogen to give 2 molecules of water. But the same that we can say about this proportion of 2 to 1 to 2 of molecules, we can multiply this proportion by a number as large as you want. So again, if we use the proportion 2, 1, 2, you can picture that this is how the reaction will happen, at least in a balanced way, alright? But again, this reaction, balanced this way, is also true, because 4 molecules of hydrogen will still react. You could, in this case, we just multiplied this reaction by 2, right? And we obtain this one down here. Right? So this is still a balanced reaction. This never means there's just 2 molecules present in the bulk. Does not mean there's 4. It's just a question of proportion. This does not tell us how many reactants we have mixed in the laboratory. Hopefully that'll become clear once we talk about leftovers and limiting reagent. The practicality of it is that actually I'm multiplying it by 2, so this would still be a balanced reaction, okay? But hopefully you all also understand that I can multiply this by the Avogadro's number, and we can talk about that 2 moles, that is 2 times 6.022 times 10 to the 23, right? 2 moles of hydrogen react with 1 mole of oxygen to give 2 moles of water. Okay, so again, I want to emphasize it's a question of proportion. Okay, so there are many ways to balance a reaction, the same way as there is for a recipe, depending on how many people are going to eat your recipe. Okay, so let's practice a little bit. One of the most important, I would say, I'll dare to say that it's the most important reaction in a cell, is the combustion of glucose. All cells use glucose as fuel, as their main source of energy. All right. So in this case, we have the combustion of glucose all the way to CO2 and water, and it's asking for how many grams of carbon dioxide will form if we start with 4.4 grams of glucose, and all of those react. The first step in these kind of problems is always balancing the reactions. We will apply the principle that the number and the identity of elements is always conserved in reactants and products. So let's balance this reaction based on that principle. We have 6 carbons here in the overall reactants, therefore I have to multiply this by 6. How many hydrogens do I have? I have 12 here, I have 2 here. I need to multiply this by 6. 6 times 2 is 12, so this means that I have the same number of hydrogens on both sides of the reaction. And finally, oxygen. In combustion reaction, this is a typical combustion reaction, which means a reaction with oxygen. You will always leave oxygen for the last one because it's alone, so it's easier to balance reactions when you balance oxygen the last one. So let's count oxygens on the right. We fix carbons and hydrogens. We have 6 times 12, that is, sorry, 6 times 2, 12, plus, and 6, no, sorry, I'm talking about oxygen. 6 times 2, 12 oxygens, plus 6, 18 oxygens. There's already 6 here. I need 12, and this will give me 2. So with some practice you will see that this is a balanced reaction. Okay, so now let's solve this problem. We have 4.4 grams of glucose. The first thing to do is to calculate the molecular mass of glucose. How can we calculate the molecular mass of glucose? So it's 6 times 12 grams per mole for carbon. For hydrogen is 12 times 1 gram per mole, and for oxygen is 6 times 16 grams per mole. I believe, if I'm not mistaken, this is around 180 grams per mole. Notice that I'm not putting decimals. If we want to give a more exact answer, we should put the decimals and work with them. But for the sake of example, we will not do it. So we have these many grams of glucose. First of all, as we said, we can work, the proportions work for atoms, they work for moles, but they do not work for grams. Let me make that clear. It does not mean that 1 gram of glucose becomes 6 grams of CO2. However, 1 mole of glucose becomes 6 moles of CO2. So we have to keep the proportion of reactions in moles. So let's convert grams into moles. And this is why we computed the molecular mass, which says that in 180 grams of glucose, I have 1 mole of glucose. And now I'm going to apply the stoichiometry factor, which tells me pretty much, so the recipe, which says that 1 mole of glucose, it's asking about carbon dioxide, how many moles of glucose will I get? 6 moles of glucose. Sorry, 6 moles of CO2. That's what it's asking. Does that make sense? This is given by the proportion 1 to 6 in the balance reaction. And now I have, so notice grams of glucose go away with grams of glucose, moles of glucose go away with moles of glucose. I have moles of CO2. I need to convert moles of CO2 into grams. What is the molecular mass of CO2? So for carbon, I have 1 is 12 grams per mole. For oxygen is 16 times 2, which is 32. So 12 plus 32 is 44 grams per mole. So 1 mole of CO2 is 44 grams of CO2. And we just need to plug this into a calculator. I really dislike this factor because I don't enjoy putting numbers into a calculator. I don't think they bring any new knowledge. So I like to give the answers like that, because any Wolfram Alpha or any website can calculate that. Okay, and at least now we know where all these numbers come from, which is what is really important for us. Hopefully that will make sense.